tip equals to what? L minus delta L. Actually, as if channel length is decreasing, right? Effective channel is getting reduced. Okay, so what will happen if due to VDS, increased VDS, effective channel length is getting reduced, then what will happen to current? Tell me.
Current will increase.
Current will increase because L is at the denominator. Very right, you are very right. So this effect is called, ideally speaking, when you take a long channel MOSFET, ID, and this is VDS. Okay, x-axis is VDS, ID is this. In long channel MOSFET, behavior of this device, MOSFET device, is for small VDS, current is going to linearly increase, and after that it is going to saturate and going to remain constant. Okay, so this is saturation region, this is linear region. Okay, now what happens if this thing happens, means if you increase the VDS, you see that effective channel length gets reduced. So what happens due to that effect, as you increase the VDS, current also almost linearly increases. This phenomena is called channel length modulation. Channel length is getting modulated or not here? Yes, tell. Channel length modulation. Channel length modulation. CLM, we call it CLM in brief. Okay, so due to CLM, we get this kind of response. This is not desirable, of course. With VDS, current should not increase, rather it should be constant. Once it is constant, then MOSFET behaves like a current source. What is the ideal current source? Ideal current source is what? Tell.
Sir, resistance is infinite, which is in parallel.
Yes, ideal current source is that source that will supply constant current irrespective of the voltage across it. Okay, suppose is a current source, here you have connected a voltage across it is varying, still current supplied by it will be constant. Current supplied by it will be constant, then it will be considered as an ideal current source. Like say if it is a battery is the ideal current source. Okay, even though its voltage maybe after some use, voltage may be dropped 1.5 volt to 1.45 volt or so. Little drop may occur after prolonged use of a battery, but still it supplies constant current. So ideal current source is your battery actually. But yes, MOSFETs also can be used. If it is a long channel MOSFET and this thing can be neglected, CLM can be neglected, then it is a constant current source. Okay, but yes, remember that you have to operate this MOSFET in which region? Saturation region, obviously. So this thing is being thought of here. So what we saw here, that we could write this expression also if the device is operating saturation region and if you can neglect the CLM. This is nothing, lambda equals to indicate the CLM. It is called channel length modulation factor. We have taken it as 0. Possibly we have taken the large MOSFET, very long channel MOSFET. By long channel MOSFET, in case of it is a very, say 20,000 nanometer, earlier it was 20,000 nanometer or 20 micrometer. During that time, 20, this little depletion region width may be only 5 nanometer, whereas your channel length is 20,000 nanometer. In that case, the 5 nanometer, delta L will not be able to affect much to the current value. Are you getting my point? Say 40-50 years back, the MOSFET channel length was L was 20 micrometer, which is nothing but 20,000 nanometer. And remember that delta L, whatever I am showing here, depletion layer width is about 5 nanometer. So the L effective for a long channel MOSFET is what? 20,000 minus 5 is not a big deal. Whereas now the channel length is only 20 nanometer. And from there, if you subtract 5 nanometer, it is a big deal now. It's very problematic. It's going to affect current drastically. Is it clear? Short channel MOSFET and long channel MOSFET, this is the problem. In a short channel MOSFET, this channel length modulation effect is dominant or prominent. Are you understanding, Aman?
Yes, sir.
So, ignoring CLM, we can write the current equation of this second MOSFET, that is Q2, this way. And equation 1 and 3 gives us this expression. If we divide current IO divided by IREF was this one, this equation. So we can get this one, which is called current gain or current transfer ratio, or IO can be written as this IO, IREF into W by L up to MOSFET Q2 and W by L up 1, that is W by L up. W means you know what is W and what is L. If you don't
Yes,
know,
sir.
ask. Yes?
Yes, sir. L is the length, channel length, and W is the width of that part.
So what will be the width in this case? Oh, that has gone. See, if I draw, once again I am drawing to show you what is the width. If you don't know, tell, I'll draw and show you. N plus and okay, this is L and this dimension is width, this dimension of the MOSFET. So are you getting? Current will be flowing in this direction. If this side is drain, this side is source, source side and drain side. So current will be flowing in this direction under the gate. Are you getting? So if width is increased, what will happen to the current?
Current will increase.
Current will increase because see, in this direction you are increasing, so current will be increasing. And if channel length is or L is decreased, then
So decrease will
Sir, increase.
increase. You can understand from the equation, but otherwise also you think of that wire. If length of the wire is reduced, its resistance decreased. So current will be more. If diameter of a wire is or area cross-sectional area is increased, resistance will be increased or decreased of a wire. Area, say you have a wire, this kind of wire. I am talking about the area here, cross-sectional area. If cross-sectional area is increased of a wire, its resistance increases or decreases?
Decreases.
Decreases. Current
Increases.
increases. Same thing here also. Area of a MOSFET is nothing but W into L. Do you understand? W into L. Are you getting my point? Area is, if area increases, what happens to the current? Anyway, we can understand separately that if W is increasing, then current will increase. If L is decreasing, current will decrease, and that's all. So coming here, we have seen that current ratio, transfer ratio is this one, and hence, if current IREF is generated somewhere, we can get equal amount of current if this equals to this. If you want higher value, then higher value of current, what will do? Suppose you keep the channel length same, increase it, so you'll get a higher value of current. Is it not possible?
Yes, sir, it is.
Okay, now I will go a little fast. So effect of VO on IO, VO on IO. We have already said that VO should be such that it is operating saturation voltage. That's what is said here. VO should be greater than VGS minus VT, which is also called VOB. VGS minus VT together is called VOB, overdrive voltage. So that is the condition to design a current mirror. Now, as mentioned earlier, once a constant current is generated, it can be replicated to provide DC bias currents for the various amplifier circuits. See, this is one point. Here may be a one circuit, amplifier circuit, right? Here may be another amplifier circuit. Yeah. So you want to bias it with a certain amount of current, constant current. So current mirror can be used to steer the currents to different locations. Here we are showing two locations, two circuits. Here it is going to sink current from this amplifier. Here, in this case of MOSFET, is going to source current. It is sourcing, okay, source current, and it is sink current. So this circuit should ensure that this Q2 is in saturation region. Similarly, this circuit should ensure that this is in saturation region. Once it is, these conditions are true, then it can be used as a current steering circuit. You can send current to this circuit or send current from this circuit as per your ratio. So we can write I2 equals to IRF, I2, this equals to IRF into W by L by 2 by W by L by 1, which we have seen in the last slide. Similarly, I3 equals to what? I3 equals to I4, of course. I3 equals to what? This I3 equals to IRF. Same tapping is there. VGS is same for this one also. VGS of Q3 and Q2 and Q1 are same, remember. So we can write this IRF equals to W by L3, that is of Q3, and W by L of 1, which is equals to IRF, I4. Same current is flowing. Okay. To ensure operation of Q3 and Q2 in saturation region, same condition, VDS, VD3, and this one, drain voltage of 3 minus, this is minus voltage, okay, minus BSS plus VGS minus VTN, and ID2 is equal to minus BSS plus VOB, okay. So this whole thing is called VOB. Is it understood, Aman?
Yes, sir.
Now, explain the application of CMOS based current mirror as current steering circuit? Substance your answer with suitable diagram. This was the question. So the current mirror found by PMOS transistor Q4 and Q5, Q4 and Q5. This is also PMOS based current mirror. Okay, same as this. Only thing this is NMOS, this is PMOS. This is towards the ground side or low voltage and negative voltage side. This is VDD or high voltage side. Okay, same way Q4 is equivalent to Q1. This is also diode connected. This is also diode connected. Since it is diode connected, it is operating saturation region. If you can ensure that Q5 is in saturation region, then can be used as a current source. Anyway, Q5 I5 here equals to I4 into, that is the reference reference current is a current mirror, and reference current is I4 into W by L of 5 and divide by W by L of 4. Same principle, same things. Are you getting?
Yes, sir.
No.
Yes, sir.
So we know also that I4 is equal to I3. So to keep I5 in saturation, the its drain voltage should be this thing. The same concept. VDS greater than VGS, something like that. You have to think of. In case of NMOSFET, for PMOSFET, it will be less than equals to. Okay. So here in figure Q2, this fellow pulls its current I2 from a load or a circuit here, and Q5 pushes current. Here it is pushing a current in this direction. It is sinking current. Okay, pulling currents. Thus Q5 is called the current source. It is sourcing the current to the circuit, and this one is sinking the current here. Okay, sinking current. Here is the example of where and how these current sources are or current sinks are used. This circuit is what? It is a source follower. How can you say that it is a source follower? I have written, so you should not say. By circuit configuration, you must say. Aman, tell.
Yes, sir. It's a common drain, and it is also known as a source follower. Or we can say output is taken from source.
Output is taken from source. It's a source follower, not from drain. Okay, is that right? You are right. So this is the amplifier circuit. Okay, amplifier circuit, and this circuit here is nothing but the Q2 of this circuit. Q2 of this circuit. Okay, this is sinking the current, and this part is that side. Q1 part is this side. Are you getting my point? This Q1 part and this part is this side. This circuit is your source follower shown there. In this example. And in this case, Q5, this is equivalent to Q5, this Q5. This is the Q5. And this is what? SCS amplifier, because output is taken from drain. Understood? These are the examples of using current source. This is sourcing the current in this direction, and here this is sinking the current. Sinking current from a circuit and sourcing current to a circuit, amplifier circuit, CS amp. Is it understood?
Yes, sir.
Okay. Now, find drain current M4 of M4. If all the transistors in saturation region, IRF equals to 30 microampere, IRF is equal to 30 microampere, and alpha equals to beta equals to 5, where alpha equals to this and beta equals to this. Is it not easy to find out? See, look at and tell me. Yes or no? ID2 equals to IRF into this, divided by this or no? This too. And ID3 equals to ID2. ID3 is flowing through this, ID3 flowing through this MOSFET M3, and this equals to ID2 is same, because There is no gate current here. There is no gate current in this direction. So whatever current is flowing through ID MOSFET 3, that is going passing through this M2. Is it okay?
Yes, sir.
Thus, ID4 equals to alpha beta IREF, where alpha equals to this, beta equals to this. By proper choice of alpha and beta, we can establish large current or small current. Okay. For example, if alpha equals to beta equals to 5, then you get this factor is going to be 25. 25 times higher current you can source here. 25 into IREF. Yes or no? How you can do that? By changing the WL ratio. IREF you are generating in one place by a precision register. That register are not shown here. Current sources symbol is shown here. Here you have a precision register. If you want less current to be sourced here, what you will do? Change the ratio. Alpha equals to beta equals to 0.2, for example. So you can get I4 equals to I ref into 0.2. Okay. Is it clear?
That is 0.4.
Yes, sir.
No, it is I4 I have written. It will be 0.04. Actually, it is multiplied by 0.2 if it is you are taking 2. I4 means current through this I4 means this and current through this MOSFET M4. Okay. I4 I am denoting this current which is being sourced to a circuit here. Maybe a CS amplifier in this and this one in this case. Q7 here. Understood. Now we'll start discussing the other version, BJT version of the current mirror. The same thing. As you can see, this is also same way connected. Base and the collector has been connected together. Okay, and this will be acting in a active mode. It was in saturation is the active mode. This also should operate in active mode, and that will be ensured by the circuit over here. Okay, but let us see what is the problem in this kind of circuit. BJT circuit. So main differences. However, there are two important differences. Firstly, the non-zero base current of BJT. The current here we are showing earlier 0, but this time it is not 0. IB will be there. Okay, that is a one difference. Or equivalently, the beta, finite beta is there. Beta of this. Beta means, I C equals to beta IB or not? You are studying somewhere or studied somewhere?
Yes, sir.
So this beta is finite. It is not infinite. If IB equals to IC by beta, if it is infinite, very large, we can say that IB is negligible to 0 or very close to 0. If it is very large, okay, but it is not the case. We cannot say beta is infinite. Okay, it is not infinite. So that is the issue. Second, the current transfer ratio is determined by the relative areas of the base emitter junction of Q2 and Q1. Base emitter junction, EBJ. What do you mean by that? Base emitter junction? Base emitter junction area. Suppose I'll try to draw it to explain this thing, but my drawing may not be so accurate. I am showing this. Try to understand. This is your emitter. This is your base, this is your collector, right? So you will have cross-sectional area in this or not? This cross-sectional area will be there.
Yes, sir.
EBJ cross-sectional area. I mean, EBJ means base emitter junction cross-sectional area. Are you getting my point?
Yes, sir.
EBJ, this area. So relative areas of the base emitter junction of Q2 and Q1 and Q2 will be deciding this current transfer ratio. That's what is said here. Let us quickly finish it up. You don't want to come back to this topic. So let us first consider beta is sufficiently high so that we can ignore IB here. Okay, we are ignoring that it is 0 initially. Okay, this is an assumption. And we can neglect the base currents, and the reference current IRF, which is here, is passed through the diode connected transistor Q1 as usual, like MOSFET. Thus establishes a corresponding voltage VBE here. Voltage will be across this will be created, which in turn is applied between the base and the, here also the same voltage will be applied. This base and emitter of this emitter and base of this terminal. Okay, same VB is being applied to another MOSFET, that is, sorry, BJT, that is Q2. If same potential is applied at the base terminal with respect to source, current to this will be also same. IO will be same. Only thing is, if its base emitter junction area is same. Yes or no? Of course, it should be operating in which region? The circuit should ensure that it is operating active mode. It is in active mode. Then we can say that IRF equals to IO if BZ is EBJ is same, and it is also operating in same. EBJ area same and operating in active mode. Two conditions: if this Q2 operates in active mode and EBJ1 equals to EBJ2, means both junction, base emitter junctions having the same area. Is it understood? Then we can write down this IO equals to IRF. Aman, are you understanding?
Yes, sir. It's understood.
Sometimes IS is called scale current. What is written here now? If Q1 is matched to Q2, more specifically, if EB's area of Q2 is the same as that of Q1, the Q2 has the same scale current IS as Q1, then the collector current of Q2 will be equal to the collector current of Q1, that is IO equals to IRF. Okay. To obtain a current transfer ratio at the unity, here we are telling that it is totally matched. Area, EBJ area is same for both. Equal amount of current was flowing, but we want more current or less current. Then there should be a multiplying factor M. That is going to be what? Actually, the area ratio. Area ratio. M will be nothing but area ratio. So we simply arrange that the area of the EBJ of Q2 is M times that of Q1. Then you can write this equation and you can get higher or lower current. This IO may be higher or lower depending on the M. In general, the current transfer ratio can be written in this way. Alternatively, if the ratio, area ratio M is an integer, one can think of Q2 as equivalent to M1, M transistors. Means otherwise also if you small BJTs, multiple BJTs can be connected in parallel, and you can get the same effect of M number of BJTs you are connecting, then also possible. Okay, going further. Now we are going to consider that beta is not so big or infinite. The analysis for the case in which the current transfer ratio is nominally unity. That is for the case in which Q2 is matched to Q1 is illustrated in this. The key point here is that Q1 and Q2 are matched and have the same dB. Their collector currents will be equal, and node equation gives us this IREP equals to IC and plus 2IC by beta. This is 2IC by beta, and this is IC by beta, this is IC by beta. This plus this equal to this. Okay. Finally, since the current transfer ratio can be now written in this way. Is it agreeable? Are you getting this point?
Yes, sir.
So note that as beta approaches infinity, this is going to be 0, and hence you are going to get what? IO equals to IREP or not? Same thing only. If you assume that beta is approaching infinity, then same thing is going to happen. IO equals to IREP. For instance, beta is taken as 100. And if you take that, then error in computing will be around 2%. The current transfer ratio error. Furthermore, the error due to the finite beta increases as the nominal current transfer ratio is increased. Means M is increasing, for example, then this error is going to increase. So for a mirror with a nominal current transfer ratio M, that is one in which I is 2 equals to M I is 1, the actual current transfer ratio is given by this IO by IREP equals to M by 1 plus M plus 1 by beta. In common with MOS current mirror, the BJT mirror has a finite output resistance RO. It is having RO, that is also having RO. RO we have defined earlier. I think in MOSFET case, RO is defined as what? 1 upon GDS. And GDS is what? Delta ID by delta VDS. In case of MOSFETs, output resistance, GDS is conductance. 1 upon that is RO. Okay. 1 upon that is RO. That is the way RO is given. Output resistance, or you can say this is because of the CLM actually. The small scale model you have defined. RO was for what? CLM or not? RO sometimes we denote it with RD. Yes? Someone?
Yes, sir. Yes, sir.
So this thing here also, output voltage divided by output current. This is your output current, this is your output voltage across drains. So this is also same. That's what is written in common with the MOS current mirror. The BJT mirror has finite output resistance. It is not infinite. If it is infinite, current will be like this, constant. Okay, it is finite, so it will be meeting somewhere. If you extend it, extrapolate it, it will be meeting somewhere. And this is due to early voltage. It's called early voltage. Early voltage. You might have heard about early voltage. It's early voltage. Thus, even if we neglect the error due to finite beta, the output current IO will be at its nominal value only when Q2 has the same BC as Q1. namely at VO equals to VB. As VO is increased, IO will correspondingly increase. Taking both the finite beta and finite RO into account, we can express the output current of BJT mirror with the nominal current transfer ratio M as this. IO equals to IRA, and here what we have done is we have taken care of this finite beta as well as finite RO. It is not infinite. Okay. If RO is infinite, this RO is infinite or RD is infinite, what will happen? Tell, current will be this way or this way? Which one? ID or IC, whatever you can say. In case of MOSFET ID, in case of BJT, it is IC, collector current. Which one is for RO infinite or RD infinite? Tell.
So at the bottom one.
Bottom one is RO infinite, RO or RD. Both are normally used in the literature. Is infinite. Okay, this is the case. This is finite RO or RD. So taking that into account, we can write this equation for IO, where we denote that error term due to the early effect, which we call CLM in case of MOSFET, is expressed in a form shown, and that shows that it reduces to 0 for VO equals to VBE. VO equals to VB, this term will be 0. So you'll left with this term only. So simple current source sink, what we have already discussed. So in MOS case, the basic BJT current mirror can be used to implement this simple current source or sink. This is going to sink in this case. We'll see the case of source also. So this is the equation which can be written. And here is the VBE. So current IREP equals to what? BCC minus VBE divided by current divided by resistance. You get this. So IO can be written in this way and RO can be as this. Is it understood? The current steering circuit, as we have seen in case of MOSFET, it is going to sink current. This is going to source current. This is a source current. This is going to sink current. Here instead of wider, I mean EBJ wider, you can use unit size double MOSFET in parallel. Two MOSFET in parallel. Here triple MOSFET. Sorry, not MOSFET. It's BJT. 3 BJT in parallel to increase the current transfer ratio. To generate bias currents for different amplifier stages in an IC, the current steering approach described for MOS circuits can be applied in the bipolar case. As an example, consider this circuit shown here. The DC reference current IRA is generated in the branch that consists of the diode connected Q1, resistor R1 and resistor R, and the diode connected Q2. This is Q2, and we can write IRA equals to this BCC, and this is minus. This side is minus. Remember, all are minus BE. So minus plus. Actually, BCC minus this. It is minus. Okay. So minus, so it has become plus. Minus BEB minus BB2. In this 2 BB is there. 1 is here. 1 is here. So divide by R is giving the IRA. This is basically, this is BCC. This is BEE minus. So potential difference between these two. Taking this potential also, you get this equation. Now for simplicity, assume that all the transistors have the same beta. Beta value is same for all. And thus the base currents are negligibly small. High beta and all are same. So beta is neglected. So we'll also neglect the early effect. That is CLM in case of MOSFET. The diode connected transistor Q1 forms the current mirror with Q3. Q1 with this is forming a current mirror, which is going to source current here. Thus Q3 will supply constant current I1 equal to IREF. If both are same, of course, it's a EBJ should be same. EBJ area should be same. EBJ 1 equals to EBJ 3. Transistor Q3 can supply this current to any load as long as the voltage develops at the collector does not exceed this value. I mean, it has to operate. Q3 has to operate in which region? Active or not?
Yes, sir, active.
Active region. In case of BJT, in case of MOSFET, it is saturation region. And for that, voltage should be VCC minus 0.3 volt. Otherwise, Q3 would enter in saturation region. That should not happen. To generate a DC current, twice value of IRF, two transistors Q5 and Q6, this Q5 and Q6, each of which is matched to Q1. This one is matched with this one is also matched with this one. So double current will be flowing. I mean, I3 will be 2 IRF. This is understood? 2 IRF. Pratham?
Yes, sir, understood.
Note that the parallel combination of Q5 and Q6 is equivalent to a transistor with EBJ area double of Q1. Instead of connecting 2, you could make that junction area double. That's what is done in case of the IC integrated circuit. The transistor Q4, this Q4 and this Q2 are forming the current sink. It is sinking the current. This was for sourcing the current. This part was sourcing the current. This is sinking the current from this and from this circuit. Circuit 1 and circuit 2. From these two circuits, it is sinking current. So, transistor Q4 forms a current mirror with Q2, and this is Q2 is direct connected. Thus, Q4 provides a constant current I2 equal to IRA. If they are all, I mean, EBJ 2 equals to EBJ 4, then it is possible. I2 will be equal to IRA. Note that while Q3 sources its current to parts of the circuit whose voltage should not exceed this. I mean to say, it is what it is meaning. It is meaning that what? Q4 sinks its current from parts of the circuit whose voltage should not exceed this. Means it should also operate in which region?
Active.
Active region. Yeah, then only it is possible. That condition. This circuit 1 should ensure that. Finally, to generate a current 3 times IRA, 3 transistor Q7, 8 and 9, each of which is matched to Q2, are connected in parallel and the combination is placed in a mirror configuration. Okay, see these 3 are going to multiply current IRA by 3. Okay, this current may be 3 IRA. Okay, if each one is equivalent to Q2. Is it understood?
Yes, sir.
Okay. With this, current mirror topics or rather module 3 is over. One call is coming. Let me take the call. Hello. Yes, Yash. Can you call me in the evening or sometimes later because I'm in the class? Okay. Okay. Yes, I'm back. What I was telling is with this current mirror, your module 3 is over. So you also can plan for the third quiz. Okay. I think your second quiz will be on Thursday, this Thursday. And this also can be planned in future. You plan it and tell me. You consider the other sections, then only decide and tell me the date. Okay. Harsh Tripathi, are you there?
Yes, sir.
So discuss with other section. Once that section is completing that module 3, then plan and give me the date and time. Now I'll be switching to the fourth module and see what is there in that module.
Sir, we have
Your time is over?
yes.
Yeah, time is over. More than time, you are not telling anything. You tell when time is approaching or exceeding, then you tell that time is over. I'll not take more time. We're in a comfortable position, so not to worry. Okay then, leave the class and join other classes.